Okay, we start recording. Welcome everyone to this new episode of EagleFly, the experimental debugger. Today we'll be continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and welcome. Today we will making the disassembler. If you have any questions, you can post them on Twitter or YouTube, and I'll be there to answer. So let's start with this, because we have something to do that we left off on the last stream, and that's time for us to go back into it. So if I open the project, I can show you what we were doing. So let's compile this, so we see that we left this on a compilation state, which we do, and then we can just say, well, the last thing we were working at is that sorry, let me open the project, the debugger, so we can see as well. Okay, so we have Winter 2 flat assassin. Oh my god. Not now, not now. Thank you. Are you asking me if I am enjoying Mr. Visual Studio? If I enjoying the experience of going into Visual Studio? Well, you know, what can I say? Probably the thing about making a debugger can answer that question. Alright, so let's see, let's run this so we can see if ever, you know, if we do something with it, you know, if we get to the point where we disassemble as before. And you know, something is gonna happen, we're gonna see what happens, you know, and we can just say that we can debug this. So we can get the ID. Now this main OpByte thing right now is let's point it's D5. That's correct, because this is a floating point instruction. So we should get that we have what is it again? 1 byte table. It's a little bit weird because D5, let me see. D5. Oh, what? Yeah. Oh no, my bad. No, that's correct. I was forget. Yeah, D5. It's a 1 byte table. It's not. It's D8 through DF, the escape output. So yeah, so I can run this again. We get the entry. I know. Let's see. We get a valid entry. Let's see. Yeah, it's an AAD. Adjust after division. Oh, okay. So let me step forwards into here, and we just say, well, you know what? With instruction, I don't care. What about the C by? Where am I pointing at? It's D8. Alright, that's correct. We're on D8. That's good. So we can just say, well, we're gonna go to D8. What happens with the 8? I don't know. Let's see. It should be. This is a floating point instruction. That's for sure. So let's go, and yeah, we have a D8 thing. So we're gonna push onto the other main OpByte which is something that we don't need anymore, but for now we're just gonna keep it like that. So let's see if we get it. We can just say yeah, that we do get it, and then we just return it. So there you go, we have that thing. And then it's like, well, we're gonna pass by there, so the entry is correct, it's a fan instruction, but well, that's okay. Now CByte now it's pointing to the next instruction because we don't need anything about this, but let me see if we do have a mother RAM, but the processing gets well, let's see what happens here. We fetch a memory operand, we have a mother RAM, we have a register operand. So we're gonna say, well, you know what, I'm gonna do this, and then we're gonna just get it by itself. And then here's the problem now, because we already passed by there, so the operand offset is gonna be busted. So we're gonna do that, and then we're gonna do the next one, and then this is pretty much the same thing. And there you go, and there we don't have an immediate, so we shouldn't get in here. So we're just gonna add the offset to the CByte. So the CByte now is gonna be incorrect, of course. It's gonna be 1 pass by, so now it's an E1. And we don't want that, of course, because this is another instruction. So we're gonna modify that as well. So we can do that pretty trivially now, because if you remember, the last thing we did was that we were working with the ID system, for the entry retrieval, because we want a unique identifier for each one of these ones, so we don't make any banana stuff. So so that's pretty much what we worked the last stream. And we got to, I don't know if it's the best hash or any, it's probably not. It's just something that we just make up there. So, but for example, where is it? Fetch memory operand, fly operand size, fly blah 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 blah. Where is it? It's on get entry index. Here you go. Well, get entry index is the one that sets it. Yeah. This is the thing. We have a value that that gets computed using the OpByte table ID and the index. So we pretty much and the reason that it works, at least for now, is because we have all those values whenever we make the access. It's like, oh, this is the thing that we get, compute the value, and that's it. This is not an indexed hash, well, how to say it? We don't get an index from the hash, we get a unique identifier. That's all. The order in it's we have an order, a straight order. We probably I don't know if that's simpler because the order it's expected, but it's just like saying, well, we have a unique ID thing system, and we already know how many they are, but we just want to have a way to differentiate across entries. So that's the way. That's why we did this. And yeah, so if we have an idea now, we can just say on the ID system, whenever we initialize the entries, over here, is that, well, we were doing this before with this banana stuff where we have different setups, because before we needed different like something that identifies them, like a uh, like um, like a thing, you know. But now, I mean, we pretty much can use it, and the idea we generated on runtime instead of having it just uh, statically, you know, loaded, or instead of just being one thing that is not sufficient, you know, in this case, which was the OpByte or any kind of other thing like the modern byte or whatever, which is not the kind of thing that we want, of course. So let's get we can change this pretty trivially. I'm just gonna see this stream now, so we can just say, well, you know, pretty much we don't even need this, you know. The only reason why we have this is because the instruction stream doesn't count throughout there, but we can even do this. And just bear with me this. Now we have the O tree. Oh, we have it the other way around, you know. So this is O3, this is O4, A4, sorry, but this one passed by there. The problem is that, yeah, we have D5. The thing where we're expecting it always is the thing that we encode it up with always. So it doesn't matter what it is, you know, it can be any value and it's gonna be okay. So instead of having all this stupid stuff, you know, we can say OpByte's gonna be OpByte index and voila, yeah. Now the problem I'm thinking through this. You know, partly we don't right now how we have it is like we do need the byte identifier, because if you remember, well, I can go back here. Since we're matching with the OpByte that we're gonna pass, you know, right now it's just like, you know, I'm passing you something, you get me something, you know, or you pass me. But if you think of it, that kind of error prone, because, you know, the user can just get us something that probably is gonna be wrong, you know. So we could try, let me see. Let me go back into here. Push by field, no. Get entry. Here you go, get entry index, get entry index, get entry. Uh, So we can stay with the modern byte. Of course, I mean it's not that difficult to get into it, of course, and it's like the kind of thing that guides through the thing, you know. It's not just. I mean, it doesn't matter. I mean, we solved the repetitiveness, you know. Now they can be repeated and everything's gonna be fine. But it's just like saying, well, what if we can just make read about having this thing, you know? So it could be something like this. But then it would be, you know, it would be something, I guess. But I think, yeah, I'm gonna keep it that way because, yeah. So it doesn't matter what we put here. The only thing is that we have to match it all the time. So if we get the main of byte, well, we gotta get the main of byte, you know. So we can get rid about this. Don't need this anymore. Just say that we're gonna have something that's the same across space and time. And since we have tables that differ groups, you know, so it's not gonna just. That's pretty much it, you know. Because you think about it, these table IDs, pretty much all the way through identify our thing, you know. It's not like, oh, you know, we have already thing, because we're not gonna have repetitiveness inside the table ID. So it was just the point of getting onto the right table, and just the entry will be easily dispatched, you know, if that makes sense. So we probably can simplify this a little bit more, but for now, I'm gonna say, well, I'm gonna remove that thing, and then I'm just gonna say, well, here we're gonna say I don't remember which ones were the modern bytes. So I believe this is O3. Then we have D5. That's correct. A4 is from here. That's correct. And then OF. That's correct. This is the main byte C3. Now this is where it changes, because normally it will be O1, so we can just say O1. And then this is 00, but this is a DD thing, so we can just say this can be like this can be like that. But this is in modern, you see. And this is So for floating points, let me remember, because here. Okay, look up samples. We're gonna see. You see here. These are the extensions. And normally, this is for the mod RAM. You know what? Well, now I think about it. Well, this doesn't get us to the point where we cannot just leave out using the mod RAM, because if you think about it, well, if you use DD, well, DD is not. DD is the thing that we already used for defining which table we're looking for. You know. But then the get entry index is just the thing that we go forwards and get from the mother M. So that's a kind of wonky thing, because yeah, we do DD, we do have DD, and DD is just getting us to the place where we want to get, but we also need some kind of this thing, like telling us, oh, you know what, this is the entry that we really want, because we cannot just get rid of this, you know, because this is the thing that tells us which is the entry, you know. It's just that way, even though like you're trying to find a way not to use it. It's just like kind of the thing that we need to do, you know. I mean, it's pretty much, this is instruction, you know. This is the thing. This is gonna be a thing that it's gonna be unique for this particular class. Okay, so even though, yeah, I mean, we can have two DDs, many DDs, you know, pretty much in the table we have as many as the table has, but so it's E1 pretty much the thing that we have to go and fetch for. So for example, O5 here, we have the thing, E1 has to be that as well. So O5, it's the mother and byte now, so it's not the NN field. Yeah, now we don't care about that thing, but it's the mother RAM. E1 and C1 pretty much the same here, mother and bytes. All these three are mother and bytes. Now this is D5, and that's it. Now the thing, I mean, the thing I'm like trying to make conscious of is like, since I just wanted to get rid about the position and stuff, you know, like even though we get to the point where it shows like I mean, this kind of wonky thing, like we're kind of moving the byte a little bit more every time, because we have to get to the right thing to place and get to the to give them to the main byte, you know. It's just that it was just a thing. So if that's the case, you know, we'll pretty much need to do this. Well, git entry index. And here is gonna be main OpByte, I guess. So this is O3, this is the main OpByte, this is the main OpByte here. A4, D5 is the main OpByte here. This is OF is the main OpByte. So it's a little bit because we have a 66 prefix, an OF, a 3A, a OF, and a C1. So this is a 3 byte opcode. So it's until OF, which we got thing. And that's okay. Here it is 01. And that's the reason why we got there. And this is VD OX05. And we have DDX05, O1. And this is DXC1, which is the same case. And that's pretty much it. I believe. I'm probably missing something there, but so let's see now what happens. What happens? So we get to C5, we're gonna get somewhere. So this is a 1 byte table. And let's see what we got here. Well, we got an ID, which I mean, and this was like the thing. I mean, probably even this ID is not even necessary at all. There you go, we have the result. because we couldn't take read about the ID itself. But what can you do? What can you do? Well, we're gonna get there. We get the result. What about it? We got the correct one. Yeah, that's correct. Then we get the begin instructions thing. You know, we print it out. There you go. It's correct. And we can just say, well, we're gonna get to the next one. I'm gonna try prefix, whatever. So C by. Well, I can even. We're over D8. That's correct. So we get there. This is a 2 byte thing here. Now the thing we changed here is like now we're just we're not gonna move anymore. So it's just gonna say we're gonna pass over there. So OpByte should be pointer. We got the result, and then main OpByte is going to be pointing towards main OpByte +1, and then the result, which is, I mean, now that I think about it, I mean, pretty much is the standard way that we should. So they collapse. So we collapse this a little bit more, you know, because I mean, this is not the problem. The problem it was like how to decide where to set the resultant pointer, which we don't have to care about that at all, because we're starting to see some play. I mean, we can just construct the way we deconstruct this stuff, you know, we disassemble in a pretty ordered way, you know, which we don't have. Even though the instructions have all these bananas, we can collapse it in like it deterministic steps, you know. It's not that crazy. So we can just say, well, we're gonna enter there. Let's see what I get there. It's a flat instruction. That's correct. That's totally correct. Begin operand C by print instruction, and there you go. Okay, let me see. We have that's the 0 now. C by, where are we pointing at? We have the D. That's correct. Now we're pointing correctly to the place where we were expecting to do this stuff. And this is another floating point instruction. So let's go and do it. So we got it, floating point. This is a DD. Pretty much the same thing here. We're just gonna try to get it. There we go, there we go. Get the result. What about the result? It's a FUCM. It's about the entry. FUCM, it has some operands over there. So we should pretty much now have an ST1, ST0. What about C by now? C by is now pointing towards DD, another DD there, you know, which is this one. That's correct. So let's see which instruction it is. You can just go and get it. You can just go and get it. Did we get a result? It's a floating point load. That's correct. And this is not gonna have any entries at all. Well, I don't remember. For input load. Oh yes, it does have. So we pretty much do the same stuff. And we load an address. Okay, that's correct. So what about C by now? C. Oh my god. Oh, OF. like except what the hell. Yeah, we're pointing to OF, that's correct. So we can just do the same stuff. We're gonna get to ooh, we didn't get the entry there. Okay, so let's see why we didn't get it. So let's rewind here. Let's rewind and uh, uh, so if we want to go fast, we can just say that you see by him. This is just for not printing all that stuff, so I can just set breakpoint there so we can just see what happens. There you go, we are on the OF thing. So let's see what happens. Get the money entry, we got the CPI. Now this probably was, yeah, because CPI what? Oh, okay, so it's the opcode. Okay, so no, my bad. So it's a two by thing, you know. So let's see what happens. So we got a table ID and okay, it's an abstention table. I didn't remember that. Let me see. OF probably, well, since it's a two thing, we probably we probably have that in here. So the problem is that we also need to move it past. Well, let me put the charger here. Hold me a second. So the main OpByte, it's just the same thing, so it's OF. But of course, for this particular case, that's not real, because the instruction has a mother byte which is 01, so we don't pass the same thing there, you know. It's just that it's a 2-byte table, and we have to also, we define that the ID will be this one, so that's the main problem in there, you know. So we have to move past by there just the same way as we were doing it on the other side. So you know that's kind of a error prone thing. So what probably that's telling me is that we don't want to do that way, you know, where we don't know, especially with when we have an abstention table and we don't, and we don't have any kind of stuff. So we probably want to collapse the data resolution that happens after that, you know. So instead of having where is it? Here. So I mean, this is totally bogus, you know, like having to move the bytes. Like this is, we are pretty sure that it's that way. But for example, the upstation table also needs some kind of stuff. But here it's kind of chunky because we have to move. We don't know. I mean, we have to move 1 or 2 or whatever. So it's just not the kind of thing they want to think about, you know. So if we go to get table ID, we pretty much have a way to do this, because we are already checking that if we are getting on to 1 or 2. I mean, we're right here, we're checking all the cases. So for example, 2 combination thing for 2 byte thing, or even 3 combination thing for 3 byte thing here. So yeah, I mean, this is gonna just define that, hey, we're getting up to an abstention table, and it will be pretty much a thing. I mean, this is the one that decides where is the function table, you know, because this is the real checker. Like, hey, please move the pointer somewhere. So we probably want to have this. So we can just say that and here we just say result table ID. and this is the same here, and here we have to just divide so that we're gonna have this, and then this, and then this is another case, so it's not a thing anymore. So I don't know how is this done, but I'm gonna keep it there on separate thing, so I can just say boom 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 over here. This I mean, this is not correct, but we're not doing this right now, so I can just do this like this, and I can just say, well, you know, this is the same thing because we're moving one pass by the other thing here. This is for the floating point thing, where the main OpByte is OF. Oh, so these are the, no, sorry, this is the abstention table. So this is the one we want to resolve. So we have 0 0 and main OpByte 0 0. So this can be a 2-byte thing, so this is correct. It will be this. And this is a 3-byte. This is a 3-byte, you know. Well, this is VX. It's not like a 3-byte, but yeah, you get the point. Because this is a 2-byte, you know. It's OF38, and then we have an F3 there. So yeah, so this is a 2 there, you know, that's correct. And here it's different stuff. Resolve. Well, I can copy. Extension table, and here is +1 just. And then this is pretty much the same. And here is a 2-byte table. So it's the same. But like this, and then here is gonna be, they can be 1 or 2. We didn't find anything that was, no, it's just 1, isn't it? So this is gonna be like this, and here is just gonna be like that. Okay, so we just break this a little bit more. So let me compile that, and let's see. Result table ID, and here is like this. Here is the same. Table ID. And here is the same. Table ID. So let me just copy all these throughout here. Result table ID. Result table ID. There you go. And there you go. Return result. So I have to return a valid thing here. Table ID result. So this is gonna change now. So we don't need that anymore. A table ID result. Table ID result, and then we just say, well, you know, we're gonna get, you know, bad. It's just bugs, and we don't need it. Just need, hey, we're gonna do that the way we were doing entry index. We don't need it as well, but here it's just gonna change. We're gonna change menu byte by table ID result, table at there you go, and here it's just the same. There you go. Here's just the same. And here is just the same. And this is table ID result ID, table ID result ID, table ID result ID, table ID result. And in that case, we don't need this anymore. We don't have that. We don't have that. We don't have anything like that. So if you see there, we already collapsed all this stuff. You know, well, let me compile. Switch ID. We don't need this ID anymore. You know, because we don't have any ID. You know, so we just need to get the table ID result. You know, so we just get, hey, please do this stuff for me, and there you go. We don't need anything of this. We just do a simple thing there. And yeah, so, and this is gonna be from the main OpByte. This can be just the cbyte now, and I'm gonna say this table ID result at of table entries, and that's pretty much it. It's not call ID, table ID, sorry. My bad. So this is just table, I guess, table. There you go. And it's just like this. just like this. What about here? Compile. I don't see there. Hold me a second. Convert argument 2 from unit pointer to unit. Alright. Alright. You don't want a pointer, okay. I got you. I got you. And that's pretty much it, you know. So the problem now, we just left them to the table ID indexer, which is just there, you know. So yeah, I mean, because he's the one that knows where the the add position should be pointing towards, so we don't have to even try to guess where it is now. Everything is collapsed. So yeah, I mean, that's pretty much it, you know? I mean, this is all the thing we need to get the mnemonic entry. So that's good. So let's see if that helps somehow. Now this is let's run it back again, and we're just gonna say, well, I don't care about that. Let's go into there, you know. Now we're gonna get to table ID. We're gonna say, well, what do we got? We have 1 byte table, and there you go. So we got a table at thing. So it's just probably the thing that we were looking for. There we go. We have a valid one. We have a table at there. We didn't move past by a pointer. That's okay in this case. And that's it. So we move by there, and we get a valid entry. We have an add thing, add instruction. Now here is where we change it now, because cbyte is pointing to the mother and byte, to the main of byte thing here. Sorry. So we're trying to find like the way that the pointer should be pointing to, you know. Since normally, I mean, what we were trying to define is like to the mother and byte, but sometimes, you know, it has to be always the mother and byte. You know, it doesn't matter what how we resolve it, even though the encoding happens to be the mother and byte. So if the problem is that for some cases we need the mother and byte to make the entry resolution, the only thing that we just have to care about is not to move the pointer, because sometimes we have some registers over there. So that's also pretty much a thing that the entry itself can define. You know, it's a little bit wonky, but probably we can do something like this, where here this is gonna be the mother byte, you know, because this guy already knows that. So the mother and by, you know, it's just a thing. This is yeah. The table ID add mother and by. Sometimes it's mother and by. Okay. So we have to make the resolution as well for that. So we're just gonna say, well, you know, where is it? We're gonna get a bunch of pointers there, but that's okay, it doesn't matter. So, oh my god. Let me find it. Get entry index, get the mnemonic entry. Get the mnemonic, get mother and by. This is a mother and by, this should be pointing there. I don't care how you get it, I'm just gonna tell you that you're gonna be pointing there. So that's it. And in here we're just gonna say, well, you know, the mother and by, it's pointing towards main by plus 3. I was just gonna say result up plus 1, but in this case it's the same, but I wanna have the same opposite all the time. So we just say mother and by, and this is the same, and then here, for example, is gonna be the extension thing. So for the extension one, we are going to say let me open this a little bit so I don't have to collapse all the time. There we go. So I was here. What? No. So yeah, this is the thing. So let me. So for the extension tables, this is gonna be the encoding is on main loop by plus 1, but that happens to be also the mother and by, which that's okay. That's the thing we were expecting to. In this case, it's gonna be the same. Now it's 2 by octable. That's why we have to move 2 here. So that's okay. This is a 2 by octable, so it's just gonna be 2 in this. Yeah, because this is a 2 for the that's correct. So it's 2 and this is 2 because we already checked it back before. Now we haven't had well, no, that's okay, because encoding, well, yeah, because this is one key thing of what's the ID, what's not, you know, probably let me think about that. No. forget about it. Yeah. Okay, so let me move on here. Result at result modern byte is gonna be, here is the 8, so the modern byte, it's gonna be the same here, so it's gonna be +1 because it's gonna be the identifier and it's gonna be the place where we want to put the pointer towards. Now it's yeah, because it's the 8 and the next one is the modern, and it all depends. So yeah, modern by, and then here we want a modern byte that's gonna be this. And just here was the modern byte, that's correct, and that's all she said. So let me just stop that, and now let's see what happens now that we solve that as well. So we're just gonna say that we do the same stuff. Oh my god, there you go, there you go. We have a table ID, boom 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 boom. We have a 1 byte with a modern byte, blah 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 blah. We gotta get an entry index, we already know that. So we got the result, and we return the result, which in this case is a NAND, and the C byte, it's pointing towards what we could say that is, yeah, the immediate thing. That's correct. So we can be printing out a valid instruction there, and then we just say, well, we can point to C byte now. C byte should be the 8, that's correct. In this case, we're gonna do something different. This is a floating point instruction, which is with the main it's a floating point instruction. Yeah, okay, there you go. We have add main byte, modern bytes, just the same stuff. Return result, get result. Do we get the entry? I don't know. It's a fan. Okay, perfect. And then the C byte is gonna be C1, that's correct. So we have fast 0 to 1, and then we can just say, well, we're gonna continue with this. Now we're pointing towards a DD instruction. It's a floating point instruction, and then we have a FUCOM, and the FUCOM, we're pointing to E1. That's correct. It's totally correct. Just bring it down, and then we can say, well, we're gonna continue now with another floating point instruction, which is that thing. I don't know what it is. Get mnemonic entry. Let's see. Well, no, why not? And this is a floating point instruction. We got that. We got entry index. It's an FLD. It's valid mnemonic entry. it's a valid mnemonic entry, and with CByte pointing to 05, it's correct. Campaign instruction, that's correct. Let's continue. Now this is OF. That's good because this is of extension table entry. So let's do and see what happens now. Let's see. So we have an extension table, and the result is gonna be moving 2, and the minute byte is gonna be moving 2. Okay. So we're gonna get the entry index. Let's see if we can find it out. We didn't find it out because the OpByte was C3, and we works okay. So yeah, that's, I don't know where it was including. We are not encoding C3 anymore. We are encoding 01, isn't it? So yeah, for extension tables, this needs to be C3 just as well, because it's the identifier. So yeah, that's the way it goes. So where is it? Let me see. Because it was this one. No, it was this one. So we have an O1. Wherever we have an O1, there we have now a C3. And then this, I don't know, this is an extension table as well. No, this is a 3. This is a 3-1. So it's not a table extension. This is a 3-1, so it has to be OF. That's correct. Here it is. And then we have 05. This is 05. E1, C1. Okay. That's pretty much the reason that we didn't find him. So yeah. Okay. So one more time. Now I can run just straight towards there. You know, there you go. We get to the right place. Let's see if we get it. There you go. There you go. This is the place we should look at it. Of course, so by now it's gonna be C3. So now we can find it. There you go. And then CByte is just going to be the same thing, so that we can just try to find it out. This is a VM resume instruction. This doesn't have any kind of operands, so we can just say that we're not gonna do anything there, you know. And here model run presum. We're not gonna move anything there, and here is just not gonna be moving anything there. And open instruction, resolve, CByte plus offer and offset. Now here the interesting thing is that CByte is pointing towards C3 right here because we didn't move it. That's correct. But the problem is that it's not gonna serve for moving the thing. So we have to change that now, since we already find that this is pointing to the mother and byte. And the mother and byte in this case encoded the extension for this instruction, which didn't have any way to do that. So it has to be the entry that controls that stuff, isn't it? Yeah. Okay. I mean, I believe this is the only instruction that we have right now. But yeah, I mean, I see where we are going, you know. I see where we are going. I see that. Okay. So the entry has to have the information, the sufficient information to tell us where to put the pointer, you know. That's pretty much the way we have to do it. Because, yeah, it's gonna be way much simpler. Okay, so let me see where I can put it so I don't forget it. So let me let me probably it's in here. Mnemonic. Over here. So this thing that we're getting from the result has to be gotten from the entry itself, you know. So that way it's gonna be something like this. I don't care about that. So we want to do something different there, but I just put it there. So for now, what I can do, since I believe it's the only instruction we have that it has an abstention for now, for this particular case, so I can just say in here, where is it? No, here, which is the one we're looking at. It should be this one, isn't it? I mean, I don't want to do this junkiness because I'm gonna forget it and I'm gonna keep it there, but yeah, I mean, this is correct, this is the right way to go, but for now I just gonna make that change so we can see the whole thing working out, and then we're gonna pass to that thing, or probably on the next one, so depends. Probably I'm gonna first disassemble another instruction which happens to have an abstention table that has operands and probably something more, so we can see that there will be a problem there, you know. So for example, let's go back another time and I'm gonna show you what I mean by that. So we're gonna get to there, you know, this is the extension one. I'm gonna get into there, I'm gonna get to the table ID, I'm gonna just go straight on to the place where, yeah, this is the one we commented out. So we're gonna say, hey, we have a modern byte on the tree. We don't have a modern byte on the tree, of course, but that's the place to go, you know. It's just like the thing we should think about. Now so now modern bytes pointing towards a place, it's pointing towards 66, which is correct if I remember. It's already pointing one pass by the instruction, which is, yeah, it's 66. Perfect. Now that's because we have a 2 thing here, yeah. So it's what, 1, 2, 3, there you go. Okay, so that's correct. We got the result, we got the valid, and we can just print it out. This being result, of course, doesn't have any operands, and oh my god, here we go. And now we're pointing towards 66, if I'm correct there, yeah. So that's gonna save it for now. Now this instruction itself is a 3-byte one, so it has a mandatory prefix there, yeah, we know that. We can just skip it. We can just go straight on to find it out what happens in here. This is a 3-8 thing, so we're gonna move since we already moved, oh no, that's correct. I mean, this is, we're in OF, but we, well, that's crazy. Oh yeah, okay, yeah, because we have O3, so we have to move 3. Okay, no, I was getting confused, my bad. Okay, that's correct. There we go. We have a table. We should get an entry index if we happen to, yeah, we do. We go pass by, we got to the mod ran by, there you go. We got the entry. What about the entry? It's a PL line R. PL line, we didn't put the R. We didn't put the R, but yeah. Entry C by, let's see what happens. Yeah, that's the thing which should happen. And now C by should be pointing towards OF, That's correct. This is the place we should be pointing. And then we're gonna go to A4, O5, O0, 0, 0, 0, 0, 0, 0. Okay, so this is a 2-byte table thing. Okay, so let's go to there, and it has an OF as well, but this is not a mandatory prefix. That's correct. And we get an entry. This entry is a shield. It's a shield instruction. Well, shift left double. We have a valid thing. CByte, it's pointing towards 05. My bad. Sorry. This is a modern byte. So that's cool. Print instruction. There you go. That's correct. CByte now it's pointing towards 03. Yeah, that's the last instruction of your stream. So we can just say REX. There you go. There you go. There you go. Get mnemonic entry. Okay. We have an add instruction. It's a valid entry. And CByte it's pointing towards 05, which is the modern byte, and just print it out. We have at EAX 0000. That's correct. It's totally correct. And now CByte it's pointing to a null. That's correct. That's totally correct. Mandatory REX just gonna happen to get a null. So it's just gonna round to infinity, and there you go. So as you can see here, we are starting to have more complexity on the way that the coding process happen. You know, like this. I mean, we're starting to have like this. You know, we're adding more data to it, more parameters, more kind of stuff that defines the way we have to decode instruction. But you know, we happen to solve, at least for now, for these instructions. And let me see. Okay, that's good. I would like to, so let me see, we have time. And we can try to disassemble one of the instructions that I was trying to make the observation about. So let's see, we can disassemble this instruction, you know, because we're pretty much sure that this isn't. I think there's even an example for that. Yeah, you have add with a 1-byte opcode of 80H is a group 1 instruction. Table X is the case that the opcode station field encoded in the modern byte for instruction is 00B. The RM field can be encoded to access a register 11 or a memory address using a specified address mode. For example, memory 001101. Okay, so yeah, I mean, we can make this add instruction. It's not gonna be a particular problem. So now let me think about it. let me think about it. It has to be an 80 for a 1 byte. So let me see. 80, yeah, it's an EVIV thing. So in media group 1, that means that it's on let me think. Well, I can see it here. It's on group 1, that's correct. And since the rec fields of the modern byte has this value, we can know that it's an instruction. Now, which operands does it have? It's gonna be something to find out, because oh, it's immediate. Okay. So it has something on the math. It can be a register, or it can be, on the modern field, it can be a math, or it can be memory, it can be register, but it's gonna come from an immediate, and the immediate is gonna be passed along from the next instruction. So it's an IV. So all of them, for example, what about 81? Because it's in IC. So let me think about it. Let me think about it for a moment. Because this doesn't tell us which instruction it is. The modern bias is telling me the instruction that we have. So I was just like trying to think about what does this mean. So let me, EVIC, I can just go, because I don't want to. Let me duplicate this somewhere. Doesn't matter. And let me copy. No, this is the one I'm looking for. This particular group. There we go. So I can just move this to the place I want. We know E because E is the thing that tells me that we have a general purpose register, which is fine. From a segment register and any of the following values: the base register, an index register, a scaling factor, displacement, whatever. And we have a V, which tells us that it's a word, double word, or a quad word in 64-bit mode, depending on operand size attribute. So does that mean it's just for 64-bit mode? And see, what does C mean? Word for 16-bit operand size, or double word for 32 or 64-bit operand size. So does that mean So this is the one that has an 8-0 thing, which is the special case. So let me go to test assembly. No, my build. And let me clean this. So I want to see the case scenario here. I can go and erase all this. I don't care about it. I don't care about it. So just gonna compiler and the assembler, and there you go. So now let me dump it. And boom. Okay, so let's see what happens to have we have 83C008. That means it's interesting because we we have this one here, which is EV. That means that the immediate is a byte, but it's an extended probably. But the modern byte is a word or double word, you know. So we probably need something bigger. So let's say just because we need something bigger, you know, 1024. What? There you go. So we have 1024. That's not gonna be a byte, no way. So we can try to do that another time and see what instruction we got now. Whoa. Whoa, we got to another place. Now we have we don't have that kind of stuff now. You know, the assembler decided not to do that, you know, with that particular instruction. So now we have 05, which is a standard way to encode the add, which has the normal add instruction and has a mother and byte with blah, and then we have now I said 1024. Yeah, 400 is 1024. That means But why do we have a 4 value? Is because now it has to match the size of the instruction itself, so now we don't have that sign extension. We have the encoding, but we have padding, but well, just the right size for the instruction to happen to have. So that was the kind of weird thing, because I mean, if you think about it, whenever you have how can I put it? I mean, I want to try to find a way to encode these instructions, EVIC. That's a little bit crazy. So, well, let's try the one that the example is telling us right now, which is okay. I mean, I was just trying to to find that instruction, but it doesn't matter. We can. This is gonna be this, and in this case has to be this. So what about now? Well, let me see if we compile it all. Yeah. There we go. One more time. So now we have a no 4, which is not the thing that we want at all. Is there a way to encode the instruction ourselves? Probably. Like, hey, I want this thing, 80, blah blah blah. I mean, we can do it in our fake assembler, but I was just like trying to see, like, hey, what's going on? What's happening. So probably I don't know. Let's try it, because it's something that's I mean, for example, this instruction AD has an immediate value that can be passed along the way, but you cannot say this, well, or this, or anything like that, because it's just that the assembler, or well, probably this assembler can, probably doesn't, but let me see. Syntax error AAD, yeah, it doesn't have the possibility. But if you remember, we have this D5 instruction, let me put it, well, it's not like that, D5. And I don't know if I can say this, but what can I say? So D5H, and here on the disassembler we have OA, which was the standard way to do it. OAH. Now probably this is not the way to do it. It's like, what the hell, are you crazy? Let me see, how can I do that on mass? because uh, dun, 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 dun. Right massum explicit opcode. For example, this is an O3C3 and the B80000. So we don't need to write machine code. The only thing we have to find out is, like, for this particular add instruction, how do we need to write that. I mean, even though probably the assembler has its ways to translate that, so it probably doesn't have the possibility to do that, but just like, hey, we want to have that option. So yeah. So it would be pretty much like, what is it? Well, here is where we are, and here is the instruction set. And this is FPU, and this is decimal, floating point. Okay, so add instruction. Okay. This is a fat. We don't care about the fat. We want the this is a fan. This is convert word. This is okay. Here it is. So for example, the one we're looking for is this 81. It has to be 81. It can have an REX, so it's 64. But this is for 80. And the 81, I don't know what this means. 0. And it has an immediate word or an immediate double word, or an 64 and an immediate 32, which is the normal case scenario. So this is a register of memory with 32, or your register of memory and an immediate 32. So the thing that, yeah, probably this means this is like, yeah, it's 000 because that's the rec field encoding on the mother RAM. So it's just like, hey, this is a special group thing, that's why we have a 0, and we have an immediate word or immediate double word. And the other case is for the byte thing, because if you have an 80, it's it has to be a byte, so it's a register memory 8 with an immediate 8, and this is the 05. We don't care about that. This is always okay. This is register or memory. It all depends on the mother RAM, on the thing that happens to have there, you know. And it's an immediate, and this with REX. This with REX, it does register memory 8, send it immediate 8 to RM8. Now well, we haven't got to REX, but we don't care about REX right now. So yeah, I mean, we can do this, but yeah, we have to make sure that, because this is a byte, so it has to be RM8 immediate 8. So yeah, let's do that, you know, and then we can do 81.0 and then 81.0 ID and blah 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 blah. I mean, we can do all the other instructions, and we pretty much have a like something, you know, something robust that, you know, has different peculiarities across it. So yeah, well, let's try to do this one. This is cool. It all depends on, we can go to the encoding as well. So let me move this a little bit. I want to go to here. I don't know if I have it. No, I'll have it here, so I can find it. Well, it's not too difficult to find it. It's not too difficult to find it. Well, probably, yeah. There we go. There we go. There we go. So this is the add instruction, and we have from immediate to register or immediate to memory. And this is the 80 thing, which has a sign and a word and the width, sorry, but the width is encoded on the thing itself. Then we have a rec if it's a memory, a rec if it's 11, or memory if it's the mod. and then we have immediate data, some immediate data, and that's pretty much it. Okay, so, and the direction, well, it's implicit because it has to always go from immediate to rec or from immediate to memory, and this is implicitly because it has the immediate to ALAX, which is something that, well, let me move this a little bit here. So I don't see that encoding. Let me see. It has to be okay. Oh, wait me a second. Okay. Yeah, remember that we have 8-0, 8-1. If it was 8-1, the width changes. If it's 8-2, then the width stays the same. 2 byte, you know. And then if it's 2, then we have a sign. That means that we sign extended to immediate data. That means that here, well, they tell me that there's an extension happens here, but that's a little bit weird. Well, it's because the REX probably, I don't know, but yeah, the conflicting, probably the REX is getting having some conflicts with that, but it's more, I mean, the basic stuff, you know, the raw stuff should be that we have a register, you know, where is it? We have a sign extension bit for the immediate if we have 2 here, you know, every time we have 2. And if we have 3, we have a sign extension, and we have for immediate, and we have a width extension as well. Which I don't remember if it was the other way around, or because we have the width. Where is it? Yeah, we need 0. It's the low. It's an 1/8. So normally it's gonna be an 1/8 in this case, and depending on the register operand size over a thing in there, we're gonna get to EAX or AX. So yeah, I mean, that's pretty much it. So yeah, this is more like the case. And yeah, remember that if we have an REX, AH, CH, DH, BH cannot be used. Such an expression defaults to the low byte. That means that we get to another copy of AL, CL, DL, BL. And it all depends within 16-bit data operations, 32-bit data operations, and whenever we don't have. So yeah, if it's set, we default. No, if it's not set, but it's used, we default to 8-bit data information. So that's the special thing about it. Now, we know it because all the add instruction, well, yeah, all the add instructions have a W there. So that's special, you know. But some instruction doesn't have the W, yo. Some of them doesn't. They don't allow that kind of possibility. So that's important to mention. So that's the reason why on 81 and 83 we have that kind of quirky stuff where V can be 16 or 32 as well, you know, 16 or 32. In the other case, it's gonna be 8 because W bit is 0. And the sign and the other thing is that we only sign extend when the immediate when we have the S bit set. We can see here. Yeah, sign extend bit occurs in structures with immediate data fields that are being extended from 8 bits to 16 or 32 bits. Now sign extend to field effect on 8-bit immediate data, that's the thing. It's just if we have an 8-bit immediate data thing, it doesn't have any effect on immediate data that it's 16 or 32, which is the case because the data is going to be 8-bit, isn't it? It's IB, and this doesn't, if you see, for example, these 81s doesn't sign extend the immediate because it's bigger than 8 bits. Only this one and this one, but this is because REX, and this is because it's an immediate 8. You sign extended for just for a particular case here. No, this is, I'm looking at bad. This is REX. Well, I don't know, but we can send extended, we cannot, but we're not, for this case, we're not gonna send extended because it's gonna be 0, 0, so let's go and do that. X0, 0, 0, and then the immediate thing, which has to be a byte, of course, okay. So let's just add it to the stream, and I think we're gonna disassemble it tomorrow because we don't have any more time. So 80 0x 80 00 80 B. There we go. Now we can encode here a memory thing. This is memory, the way we encode it here. Probably we want, it can be memory or register, because if it's memory, we have to have a memory thing here, isn't it? Like a memory operand with an effective address size, yeah. Yeah. So if it's a memory but it's an 8, that means that if it's memory, it's the effective address size that defines it, isn't it? Let me see. Yeah, you will need the modem, and the modem will need to have an SIB, isn't it, to have that kind of encoding. But we don't have 8-bit addressing forms at all. we just have I mean, we can even try, but well, I'm just gonna command this for now. We can just say 0 0 whatever. You know, add whatever here is gonna be AL times 0 plus displacement or let's just say that we don't need anything. Which, I mean, if you think about it, it's not probably possible. And this is G135. Yeah, invalid use of raster. It has to be these ones, you know. So yeah, I mean the size is just for the effective thing, because the address has to be one of these addressing modes inside the mod RAM. So which one it is? It's a little bit weird. It has to be rather 16 or 32. That's all we got. For example, let's say we have that, you know, bx, well, it's gonna be 0 0 plus psi must be index or base register. You mean that? Or if I just say, hey, we have SI, it probably is not, because the effective address form is 32. What about BX? So EBX is gonna be possible. we cannot do that. It's a little bit weird, isn't it? So just I want to make sure that I'm reading this correctly. Yeah, we have to read this. But yeah, I mean I'm gonna stop here because I gotta go. But we got a decent thing to do. Let me just say that we have that. And this is not important. We need that. There you go. So if we run this again, we should get a standard thing happening here. Okay, that's perfect. So yep, I would say please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Yeah. Please make your questions related to the thing we did today, and I'll be happy to answer. I would say thank you very much for coming, and I will see you all on the next stream. See you all.